Okay, guys, so let's go ahead and go over this study guide for kinetics. So the first question says to define activation energy and tell what it is used for. Well, first of all, the abbreviation for activation energy is a capital E for energy. And the reason why that goes first is because energy is used in a lot of disciplines in science, physics, chemistry, biology, and it's just a standard abbreviation for energy. And then activation, since that's a specific type of energy, gets a little a underneath it. And so activation energy is the minimum, so minimum amount required to activate or start a reaction. Okay, so that's the minimum amount needed. So let's say that the activation energy for a reaction is 500 joules, but you add 600 joules. Well, because that's more than 500, your reaction will occur. But if your activation energy is 500 joules and you only add 490 joules, well, that's not enough, and so the reaction will not occur. Remember, energy, the correct amount of energy and the correct orientation are both required to start the reaction. And so if we look at number 2, it says draw an exothermic energy diagram. Now these energy diagrams we talked about last unit, and we've brought up a lot in the videos for this unit. So for an exothermic graph, okay, we know that the y-axis is the potential energy, and just as a review, there are two types of energy in chemistry, kinetic and potential. Kinetic energy talks about how the molecules are moving, and then potential energy is energy stored in the bonds. And so we have potential energy and time on the x-axis. And so for an exothermic, we know exothermic means energy overall is released. So that means your reactants kind of start out low. So I'm going to write reactants here. They absorb a certain amount of energy and then produce the products. Okay. And so they wanted us to label a few things. So the energy of the reactants. The energy of the reactants, or delta H of reactants, is the distance from the line to 0. Okay, that's how much energy is stored in the bonds of whatever reactants you have. The energy of your products is from the line where our products are down to 0. That's how much energy is now in the bonds after the reaction has occurred. And so we can see that it goes up. Okay. The activation energy is from the top of the hill all the way down to wherever your reactants are. Okay, that's our activation energy. So the transition state, and that's a unique one. Let's say our reactants are A plus BX, and what we want to form is AX plus B. So it's a single replacement reaction. A is going to come and kick B out, bond with X. Well, we know that they have to have the right orientation. And so in order for them to react, what's going to happen is you're going to have a transition state, and the transition state occurs right here at the top once the activation energy is met. And in this case, the transition state would be where the A is starting to form bonds with X, but X is still kind of bonded to B. Okay, this right here would be our transition state. It's the state of the molecules, because bonds don't automatically form just like that and then break. They have to slowly form and break, and there's a molecule that forms in between those things, as seen in this red drawing that I drew. Yeah, so one thing to keep in mind is I like to use the idea of a ball rolling up a hill to help with this image of activation energy. So if I have a ball, so let's say the ball is right here, okay? If I kick the ball and it only goes halfway up right here, then it will fall back down on the reactant side, right? In order to turn the ball into, in order to turn the ball into the product, you have to give it enough energy to make it get up to the transition state and begin to roll down the other side, okay? Now, number 3 says draw an example of molecules colliding with correct orientation. Well, in order to do that, you kind of have to have a reaction or like what you're trying to form. So let's go with what we have earlier in problem number 2. If we have A plus BX and it's producing AX plus B. Well, in order, we see that the difference here is that the A needs to be bonded to the X. And here we have A and X. So that means if this is a three-dimensional thing, because atoms are, we have A, well, it's going to have to hit and collide with the X atom as it's still attached to B. Okay, and this would be the correct orientation. But if you have A and it collides with the B atom that's attached to X, well then this would be incorrect. They would just bounce off. A can't react with X if it ends up colliding with B. Okay, you have to collide in order to react. So if the two things that you want to combine don't hit each other, then that is an incorrect orientation. So let's look at number 4. Which has a longer rate of reaction? A substance with an activation energy of 40 joules or 500 joules? Well, I like to think of this as a picture. Okay, so let's say we draw our two graphs. Okay, they both start out, their reactants are both starting out at 50. Okay, but the activation energy for the first one is only 50 joules. Okay, right there, only 50 joules. So that's up to 100, 50 more. But this one is 500, so it goes all the way up here and releases, and all the way up there, it's 550, because the difference between these two has to be 500. Now, if you put me at the bottom of this small hill and at the bottom of this tall hill, and you tell me to run up one of these hills, y'all know me, I'm not going to be the most fast person that you have ever seen. So if you give me a short hill, that will go faster for me than this long one. So when we're looking for the one which has a longer rate of reaction, which one's going to go slower? That'll be your 500 joule activation energy. Think about it, that's a mountain in compared to 50 joules. So it's going to take longer. Okay. So an enzyme, remember we talked about enzymes in your body or in your notes, but they are in the body, right? And they are the catalyst that are in your body. And it is a catalyst because it lowers the activation energy. Okay, so if we give that same scenario that we had just a second ago with me running up the hill, let's say we have that 500 joule hill, right? A pretty big activation energy, and I'm supposed to be running up this hill, okay? But as I begin to run, I see Miss Michael, she's my catalyst, she provides a shortcut, okay? And this shortcut is so much shorter. So the blue one is with a catalyst. Well, then it speeds up my reaction because I don't need as much energy and I can go faster. I don't have to go all the way to the top of that hill. Okay. And then now when question 6 asks, why are catalysts not written as a product or a reactant? Well, there are key things about reactants, about catalysts. So one thing is catalysts are not used up. Okay. They speed up the reaction by lowering the activation energy, right? That's the thing. So if you look at a reaction of A plus B is C plus D, we know that it's at the beginning, right? We have it at the very beginning, but we also have it at the end. So if it's present in the beginning and at the end because it's not used up here, okay, then it is not part of the reaction. It just speeds it up. So normally you would see the word catalyst or the specific type of catalyst written over the arrow to indicate that it's not a reactant and it's not a product. It's just kind of in the thing, in the test tube or in the beaker, to be a presence that will speed it up. Okay, so let's look at number 7. List 5 factors that result in the reaction, in the increase of the rate of reaction. Which one only affects the rate of reaction of gases? So this came from the video that a lot of us watched. If you take a look at one of the videos on this playlist, it's from TED Ed and it's called How to Get a Date and Speed Up a Chemical Reaction. It lists and has some really fantastic animations for the 5 factors that result in the increase of the rate of reactions. And so the first one is by decreasing the volume. And this is because if you decrease the volume, that means that you have a decrease in space, or a smaller amount of space. If you have a smaller amount of space, then you'll have more collisions, and more collisions mean more reactions, and it'll go faster. The second one is by adding more particles, which is the same thing as increasing the concentration. And this is because the more you have, the more likely you are to bump into someone. We know that if you are walking in the hallway during the middle of the class change, there's a ton of people out there, so you're likely to bump into someone. But if it's in between classes and you're just going to the bathroom during class, you shouldn't be bumping into people in the hallways. The third thing that you can do is increase the temperature, because increasing the temperature increases the average kinetic energy of the molecule. And if they move faster because they have more energy, then it is more likely to overcome the activation energy barrier. The fourth thing that you can do is, so surface area is number 4. If you increase the surface area, and if you can hear that bell ringing in the background, that's because I'm at school. So if you increase the surface area, meaning if you have smaller particles, okay, smaller particles will just be able to collide more often. They'll be more exposed. And so again, more collisions equal more reactions, and it will move faster. And the fifth thing is pressure. And pressure is only affected or only affects the reaction rate of gases. And this is because pressure and volume are connected. So if you increase the pressure, that's the same thing as decreasing the volume, and so less space, meaning that they will have more chances to collide with other atoms. Okay, so let's look at number 8. It says compare the rate, which remember is speed, of 12 molar HCl with magnesium and 6 molar HCl with magnesium. Which reacts quicker and why? Well, let's think about it. We know that reactions happen when things collide. So let's draw 2 beakers, one with 6 molar and one with 12 molar. Okay? If I have 12 molar HCl, so 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So 12 green dots. And 6 molar has 6. 1, 2, 3, 4, 5, 6. And I just add a strip of magnesium in there. This is going to be my strip of magnesium. It's all a solid. Just add it in there. Okay. Which one is going to have more collisions and therefore react more? Well, the one with 12. There's 12 dots. It can collide with the magnesium strip a lot more than the one with only 6. Okay, so we know that 12 molar reacts faster because there are more particles to collide with. Okay. Now, number 9 says to consider Le Chatelier's principle. Now remember, Le Chatelier said that when a system that is at equilibrium has a stress put upon it, it will shift in such a way that to relieve that stress. Now, when we have our phrases with deciding which direction the reaction or equilibrium will shift, we've been talking about 2 different phrases in class: add, away, take, towards. And so if we use this phrase, this is going to be our general rule. Let's look at the reaction. A plus B produces C plus D. Now remember, that reverse arrow, that back and forth arrow, what that means is that you could write this reaction as A plus B produces C plus D, and you could also write C plus D produces A plus B. Okay, the way it's written up here, this is the forward reaction and this is the reverse, but they're both happening. Okay, so I just wanted to go through that real quick. So if we have this reaction, let's say we add more of the reactant. So number 1, add reactant. Okay, well, if I add more of, let's say, B, equilibrium will shift away from wherever that is. So because B is on the left side, it will shift, so EQ, equilibrium, will shift away to the right. Okay, if we add a product, okay, then equilibrium will shift away, which is to the left. And I'm realizing now as I read the question that this was all about adding and that this take towards part should be written for number 10. So this one will be take towards. Both start with T. So again, take towards. So if we take a reactant, it will shift to them, so to the left. But if we take a product, for example, if we take some of C from the reaction in problem 9, then it would shift towards it to the right. Okay, so please make sure I posted a video about Le Chatelier today, and posted a couple the other day from the Fuse School that are awesome, but let's keep going. So which way does a reaction shift when you heat it if the reaction is endothermic and then exothermic? Well, let's draw what an endothermic chemical reaction looks like. So endothermic means that heat is absorbed. So that means you have A plus B plus heat produces C. Let's just do that. And then the reverse would be exothermic. C can decompose to A plus B plus heat. So this one is endo, and this one is exo. Well, if I add heat, right, because I'm heating it up, so I'm increasing the temperature. If I add heat, it will shift away from that, so the reaction will shift to the right. And if I add heat in an exothermic reaction, it will shift the opposite direction, away from it, add away, which would be to the left. Now, if we look at number 12, it says, if you have the following reaction and you want to turn it green, list at least 2 ways to make it happen. Well, let's make one of ours be something we add. And, well, let's see, we could add, if we want to shift it green, we could add away. So we could either add aluminum or add copper sulfate. Or we could take the copper out, which would shift it towards that side, or we could take out aluminum sulfate. So if you take the products or add more reactants, that would continue to make the reaction green. Now, let's look at what a definition of equilibrium might be. So equilibrium is when the forward and reverse reactions are happening at the same speed. And what this means, or what this looks like, is if you have a zoomed out approach, it looks like no change is occurring, even though atoms are still reacting and colliding. Okay, so let's look at number 14. In an exothermic reaction, does adding heat shift towards the reactants or the products? Does it take a lot of heat or a little heat? When gases are involved, if you increase the pressure, which way would it shift the reaction? Okay, so this is kind of a combo one here. So if we have a reaction A plus B produces C plus heat, right? Because it's exothermic, it's being released. If we add heat, it will shift to the left, right? Add away, shift to the left. So what direction does it shift? To the left. Now, when it asks, does it take a lot of heat or a little heat? It's going to take, in order to cause a shift, it's going to require a lot of heat. Okay, I mean, not like so much that it never happens, but we know that if it starts to warm up, for example, we did the Le Chatelier lab on Tuesday, we know that when we put the test tube in the hot water bath, it didn't automatically go from blue to green, right? It had to heat up a little bit more. There was a certain amount of energy required to make it shift. Kind of like if you were to think about equilibrium as how you feel when you're just kind of like chill, you're like everything's going good, right? And you walk into the classroom and you find out you have a quiz or a lab to do that day that you didn't know about. Well, that's a little bit stressful on your system, but usually not enough to make you go like berserk and freak out in class. However, if you were to walk in and you find out that you have your final exam that day and you had no idea, you thought it was the next week, well, that's enough to make you kind of freak out, right? It's enough to disrupt your equilibrium. You do have to have a decent amount of energy to cause that shift. Now, when it says when gases are involved, if you increase the pressure, which way would it shift the reaction? Okay. So gases are, let's say we have carbon dioxide, okay, which is a gas, is produced when carbon monoxide combines with oxygen gas. Okay, now the G here in parentheses tells me that's a gas, and before I go any further, I need to balance this equation. Okay, so 2 carbons, 4 oxygens, 2, 4. Okay, perfect. Balanced. Now, if we look, then we'll see that on the left side here, we have 2 moles of gas, so 2 moles. Whereas on the right side, I have 2 moles of carbon monoxide and 1 mole of oxygen, so that's a total of 3 moles. Well, if I increase the pressure, that means, like if you think about maybe a syringe, if you push on the syringe when you're giving someone a shot, or you're using it maybe to season a turkey at Thanksgiving, you are decreasing the amount of space that's in there. So if you increase the pressure, you have less space. You have a small amount of space. So if you have a small amount of space or less space, then you want a small number of moles. Okay? And so equilibrium will shift towards the left because that has the smaller amount of moles. Okay? Now, if the right side had a smaller amount, it would shift that way. It doesn't matter which direction it shifts as long as that side has a smaller number of moles of gas. If I had in this reaction plus 4 aluminum solid for some reason, because this is a solid, it doesn't factor in to how it will shift based on pressure. Pressure only affects gases. Now, number 15, when products are added to a reaction, which way does the reaction shift? When reactants are added to a reaction, which way does the reaction shift? That question has already been answered, so I'm not going to go over that. But let's look at the last couple ones. So define Le Chatelier's principle. A system at equilibrium that is placed under stress will shift to relieve the stress. Okay, and we kind of went over that earlier, plus that's in your notes. Number 17 says, in an exothermic reaction, which requires more energy, the products or the reactants? In an endothermic, which requires more energy? So that's kind of a confusing wording of this, I'm not going to lie. But if we were to look at an exothermic graph here and compare it to an endothermic graph, oh, this is, oops, I actually drew it the other way around. That's endo. this is exo. When they're saying which one requires more energy, they're talking about your activation energy, how much requires more to get started. And we can see that an endothermic reaction has a much higher activation energy than exo. So endo is higher, but it does say the products of the reactants. So let's talk about that as well, I guess. So if we're looking at the reactants here, in an endothermic graph, the reactants are smaller than the products, right, in terms of their amount of energy. The products are this big green arrow, the reactants are this little one. Whereas for an exothermic graph, the reactants have more potential energy than the products. And then B, when is activation energy required for a chemical reaction to occur? Every time it collides? I'm not 100% sure what Miss Mullen wanted from this question, but let's see, anytime a collision occurs, they have to have it. It has to happen at the beginning, and a transition state only occurs after the activation energy has reached. It's at the top of the hill, right? So on a potential energy diagram, okay, the transition state will occur right up here at the top. And activation energy is required for all chemical reactions. And it's got to be initial. It's got to be put into it from the beginning. So that would be your study guide. So hopefully between this and your other videos, you are going to feel ready for your kinetics study guide, or test, have a good night.